Emerson, Sir Emerson, magandang
Alas-
hapon.
Good morning, Sir B. Pag-grade ba kami?
Yung kanina, ma'am?
Oo.
Oo nga, yun nga.
Kasi siya.
Oo.
Speaker for...
Pwede na lang natin kasi may
Okay.
sinuman eh. Apa.
Okay. Thank you, Doc.
Thank you po. Sir Emerson, could you share po yung presentation? So let's try to see if everything is working well.
Okay, sure.
As we wait for the third panel member, which is Dr. Patrick.
Alright, sir. Okay. I'll be sharing my screen now. Okay. Please confirm, sir, if you can see my screen.
Yes, yung video po.
Video.
Try natin yung video
Alright.
para yung audio ma-check.
Okay.
Good day to the respected panel and advisors.
Okay, working well naman po.
Okay.
Wait lang natin si Dean Arnold to join.
Alright, sir.
Doc Jen, was trying to reach out din Arnold kasi hindi pa siya nagre-reply. So since si Doc Jo naman yung panel from last time, may I suggest po to proceed na with the presentation.
Yeah. Go ahead.
Okay, sige po. So, good afternoon, good morning everyone. So, my advisee, Engineer Emerson Cumlat Jr., will be presenting his final practicum entitled Smart Optimization of Fiber Optic Network Design using Prim-Dijkstra algorithm. So, he has the pre-recorded video presentation ready, but he will start muna with a summary of all the revisions. Sige, if you are ready, Sir Emerson, please proceed. Thank you.
All right, sir. Thank you. Good morning, dear panelists. Before we proceed with the recorded video presentation, I want to share with you the summary of revisions that I have made based from the previous meeting with the panelists. So first, I want to present recommendation from Sir Arnold. First is he wants me to include this OMCR, Objective Methodology Conclusion Recommendations, and which has been reflected on the updated amended write-up script. I've included this, and these are the relevant page numbers according to this recommendation. The next recommendation they've asked me is to include a Gantt chart for me to tell how long it took me to make this research, and I've come up with a 13-week schedule starting from week first up to this week, which is reflected on page 53 of my write-up. The next recommendation is coming from Ma'am Jen. She asked me to explain all the parameters that will be required, and I have included that on page 37 of the manuscript, and I've come up with these parameters that needs to be optimized on this research, and this will be discussed later on during the video presentation. The next recommendation, she asked me to explore optimization of hybrid topology, and yes, I've included this discussion, and it has been reflected on page 75 of the manuscript. This is a combination of all topologies and the relevant advantages of using this, and it has been implemented on this on my case study. Another recommendation is to include the link budget computation, the equipment description, and the losses, link loss that has been required to be shown onto this research. So yes, I've added this onto my recorded video presentation. That also reflects on my write-ups, and these are the relevant page numbers. Page 56 discussed about a power budget consideration. Page 72 discussed the link loss calculation of the case study and the optimized output fiber network. And fiber network equipment components are reflected on page 73 and at appendix A of this of my write-up. So appendix A also includes image of what are these equipment looks like, and the specifications for individual components. Another recommendation. She told me to use a computational algorithm for efficient route planning, and we have included that on our review, on our improvements. So we come up with these values, which are all reflected on page 71 of my write-ups. So yes, we come up with efficiency improvements after applying the algorithms on the fiber network design. And last recommendation from Ma'am Jen was to evaluate the cost effectiveness and scalability of the finished output fiber network design. So this is reflected at page 78, and it has been tabled according to the parameter that has been discussed on the write-up. Sorry, there's another recommendation from Ma'am Jen, which is to include instead of 20 nodes, she asked me to use 100 nodes, and I have selected an area in Pasig City, which I come up. I've selected this area because I find that the street view is available on the site, and I find a need for fiber network design on this area that can be proposed to the LGU or other ISP providers. So this is the main topic of my case study, and it's reflected on page 53 and 54 of the write-ups. And the recommendation from Ma'am Jocelyn is for me to remove the abstract, and yes, it has been removed on the write-up. And the last one,
Wait. Sorry ha, yung abstract should be included doon sa final docu ha.
oh
So
sorry,
if you move it, balik mo siya. It's kasi yung comment ko is for the proposal.
all
not
right,
for
sorry.
the final. So
Okay.
abstract is included in the final document.
All right, okay. So I'll reflect that on the final write-up. So I'm expecting more amendments after this defense before I come up with a summary on my IE template submission. So the last recommendation is for me to follow the correct format, which I have complied. So I've referred on the guideline for the preparation of master thesis. I use the right font size, spacing, the right spacing, and followed the recommended style thesis format, and it has been reflected through the whole page. So that's all, ma'am. If you have any questions or added recommendation, just to let me know. Just let me know. So if not, then I can proceed to the video that I have prepared, sir.
Yes, please proceed.
Okay.
Thank you.
Good day to the respected panel and advisors. I am Emerson de la Cruz Cumlat Jr., a Master of Engineering in Electronics Engineering student at Mapua University. And today, I will be presenting my final defense titled Smart Optimization of Fiber Optic Network Design using the Prim-Dijkstra algorithm. Drawing from over 7 years of experience as a fiber network designer here in Fiji, this research addresses a real-world design challenge by applying algorithm-based solutions to improve efficiency in fiber optic deployment. This presentation is structured into 5 chapters following the paper's write-up. Let's proceed on the first chapter, the introduction. Fiber optic technology offers numerous benefits, including high bandwidth, reliability, and security. Key factors for modern applications like cloud computing, Internet of Things, and high definition media streaming. Conventional copper-based networks, once adequate, now face challenges in supporting emerging technologies. The shift from copper infrastructure to fiber optic networks is driven by the demand for high bandwidth, reduced latency, and enhanced reliability. Despite its advantages, fiber optic deployment faces significant challenges, including high installation costs, complex infrastructure requirements, and geographical constraints. However, traditional network design methods often result in high costs and inefficiencies, necessitating the development of smart optimization strategies. As a fiber designer, we rely on manual and heuristic-based planning, drawing from experience, predefined strategies, and practical judgment without the aid of automated tools. The need for cost-effective, optimized solution in fiber optic network design arises from the necessity to minimize infrastructure cost while maximizing performance. Smart optimization methods help achieve this by utilizing advanced algorithms to reduce network deployment cost, improve resource utilization, and ensure scalability for future growth. During my research, I discovered two advanced algorithms, PRIMS and Dijkstra, that have yet to be applied to enhance fiber optic network design. This prompted me to explore these machine algorithms to achieve my goal of optimizing fiber optic network designs. Moreover, this study aligns with the United Nations Sustainable Development Goals, particularly SDG 9, the Industry, Innovation and Infrastructure, and SDG 11, Sustainable Cities and Communities. Enhanced fiber network deployment supports digital inclusion, economic growth, and the sustainable expansion of urban and rural infrastructure. This study centers on optimizing fiber network design in urban and semi-urban settings, where complex, dense node distributions present greater opportunities for improvement, unlike rural networks, which typically follows simpler and less optimizable paths. The scope is limited to the optimization of existing fiber optic infrastructures and their enhancement through machine algorithms. We move to the second chapter, which is the review of related literature. A fiber optic network transmits data through optical fibers using light pulses. It is typically deployed in architectures like point-to-point or point-to-multipoint using passive components, meaning there are no electric devices between the transmission ends, only at the starting and receiving points. The implementation of a fiber network starts with the planning and design phase, which involves conducting site surveys, selecting an optimal topology, and obtaining required permits. This research specifically focuses on that initial stage, planning and design, prior to the physical deployment, installation, testing, and activation of the network. Fiber network topologies define the structural layout of fiber optic connections, influencing factors such as network reliability, scalability, and cost efficiency. Common topologies include point-to-point, star, ring, and mesh configurations, each offering unique advantages in terms of redundancy, cost, data flow, efficiency, and fault tolerance. Designing a large-scale fiber network requires a careful consideration of factors such as network topology, scalability, and redundancy to ensure long-term efficiency and reliability. Designers must also account for geographical constraints, budget limitations, and regulatory requirements to optimize deployment while minimizing cost and maximizing performance. One notable previous study on optimizing fiber optic network design is CommScope's fiber indexing approach, which simplifies a typical 240 ohms distribution setup by replacing the traditional 20,000 star topology cable layout, where each terminal, the blue circles, serves 8 ohms with a more efficient design. With fiber indexing, the total cable usage is significantly reduced. This technique utilizes a linear daisy chain topology where terminals serve multiple functions. As a result, the total cable length decreases to 5,500 feet. Another ongoing research effort explores hybrid network design, which combines passive optical networks and active optical networks to optimize performance, scalability, and cost efficiency. AONs use a point-to-point connectivity that require more cabling and power, while PONs rely on unpowered splitters to serve multiple users from a central office, reducing energy use and overall deployment costs. Most existing studies on fiber optic network design addresses either cost reduction or performance improvement in isolation, underscoring the need for an integrated optimization approach, which this research aims to address using the proposed machine algorithms. My research conceptual model begins with the input, which is the initial fiber network plan. This plan will be processed using Dijkstra and Prim's algorithm. The resulting output will be an optimized fiber network design, which will be then evaluated and compared. This study targets key optimization parameters in fiber network design, such as cable length, deployment cost, and link cost, while preserving path redundancy, minimizing segments, hops, and pole usage, ensuring faster and cost-efficient deployment through algorithm improvements. Prim's algorithm is used to construct a minimum spanning tree by starting from any node and repeatedly adding the lowest cost connection to a node not yet in tree, avoiding loops and ensuring all points are connected at minimal total cost. Fiber optic networks, where nodes represent devices like switches and edges, represent fiber links, weighted by factors like distance or cost. Prim's method effectively minimizes bridging cost by optimizing the layout for efficient and economical deployment. The flowchart outlines the process of starting with an initial node, adding it to the tree, and repeatedly selecting the smallest weight edge to connect to an unvisited node, an approach that can be implemented as a C++ program. Dijkstra's algorithm efficiently finds the shortest path between 2 points in a network by iteratively exploring connections and updating the shortest known distance to each node. This method is crucial for optimizing fiber optic networks, ensuring data travels the most effective route to minimize delays and enhance performance. The flowchart begins by assigning a distance of 0 to the source node and infinity to all others. Then repeatedly selects the node with the smallest relative distance, updates neighbors, and marks it as visited until all nodes are processed. This logical sequence can be translated into a C++ program. We move to the third chapter of this practical research, which is the methodology. So this scenario presents the design of the implementation of a cost-efficient and high-performance fiber optic network intended to connect 100 fiber access nodes for an internet service provider within the Pasig area, specifically covering Barangay Mapua and Rosario, serving approximately 1,600 households. The ISP may be a private entity or a local government entity. Each node functions as a fiber access point, delivering a high-speed internet up to 16 households. The primary objective here is to reduce the overall cost of fiber optic cable deployment while ensuring full node connectivity and optimized data transmission route. To achieve this, a combination of Prim's minimum spanning tree algorithm and Dijkstra's shortest path algorithm is applied. This fiber network design follows a single line diagram starting from the optical line terminal, the OLT, and ending at the optical network terminal, the ONT in homes, with passive components like the optical distribution pin, the fiber distribution terminal, the access terminal box, and the network access point, including a 1:16 splitter, enabling the distribution of optical distribution signals to a 16 household without any active electronics in between. This illustrates how each network access point is individually connected to the optical line terminal. A tabletop survey was carried out utilizing Google Maps, Google Earth, and Google Street View to precisely identify the locations and assess the conditions of existing utility poles. The collected data was then digitized and used in AutoCAD for drafting and designing the fiber network layout. Key parameters obtained include cable distance, node positioning, splitter setup, and projected deployment costs. The Gantt chart presents a 13-week structured timeline for the practicum research, covering literature review, data gathering, network design and optimization using the Prim's and Dijkstra algorithms, performance and cost analysis, final writing, and culminating in the defense presentation and manuscript submission, ensuring a systematic and efficient progression aligned with the academic and practical goals. This is the visualization of a graph representing a region with 100 nodes. The total length of the vertices, which represents fiber cable length, is 15,648 meters. We represent the distance between nodes in a matrix format, which will serve as an input for our program. For instance, the distance between node 80 and node 81 is 109 units, shown in the matrix at row 82 and column CD, while a 0 in other cells indicates no direct connection between those nodes. This is the C++ script and program for Prim's algorithm. This represents the final program output with the data successfully exported into an Excel file format. Prim's algorithm is applied to the constructed graph to determine the minimum spanning tree. This algorithm identifies the subset of edges that connects all nodes with the minimum total weight, ensuring a cost-effective network, and the total vertices length after running the Prim's algorithm program is 10,433 meters. This is the C++ script and program for Dijkstra algorithm. This represents the final program output with the data successfully exported into an Excel file format. This diagram illustrates the application of Dijkstra algorithm to the heuristic network design. Starting with all nodes distances set to infinity except the source node N0 at 0, the algorithm iteratively selects the node with the smallest tentative distance, updates its neighbors, and marks it as visited until all nodes are covered, resulting in a total fiber installation cost of 11,835 units based on the sum of the selected edge weights. Fiber optic cable and related accessories is one of the most expensive components in network deployment. Optimizing cable usage through efficient network design can significantly reduce overall project expenses. At a high level, estimate the cost of passive components including fiber cables, ducts, splice joints, and installation is approximately 400 pesos per meter. The estimated cost for electronics component, specifically the OLT, the optical line terminal, and the ONT, the optical network terminal, is approximately 200 pesos per meter of fiber deployment. We allocate 50 pesos per meter to cover project contingencies, management, and testing. This brings the total estimated cost per meter for the project to 650 pesos, which will be used as the basis for all cost calculations. The link loss formula calculates the total optical power loss in a fiber link by summing losses from fiber attenuation, splices, connectors, and splitters. The link loss calculation is derived from the heuristic-based design, taking the farthest node, node 87, relative to the OLT as the reference point. The total loss of 16.74 dB, accounting fiber length, splice points, connectors, and the splitter, remains well within the acceptable limit of 28 dB for a Class B plus optical system. Next chapter discusses the results and the expected output. As observed, the optimized optical fiber network design has significantly enhanced cable dimensioning by minimizing cable requirements and eliminating unnecessary routing, all while maintaining household coverage and preserving redundancy links between nodes. Heuristic designs often appear irregular with redundant path. Prim's algorithm forms a loop tree, minimal length tree. Dijkstra creates efficient, centralized path from the source, focusing on shortest routes. The route efficiency is significantly improved with algorithmic optimization. Dijkstra achieves a 24.37% gain, and Prim reaches 33.33% compared to 0% efficiency in the heuristic design. In terms of link loss, at the worst case scenario, that is the furthest from the node, from the OLT, the heuristic approach result is over 0.15 dB more loss than the optimized approach due to a longer fiber length. Both methods use the same number of components, splices, adapters, and splitters, but differ in total cable distance. By applying optimization algorithms like Prim's and Dijkstra, the overall fiber length is reduced, which decreases propagation delay and improves network responsiveness, especially in latency-sensitive applications. The algorithm reduces cable segments while maintaining a redundancy path, forming a ring topology that minimizes downtime in case of a fiber break. The cost of reduction analysis shows that applying the Prim's Dijkstra optimization significantly lowered overall deployment costs by minimizing cable lengths and unnecessary routes. The optimized fiber network designs using Dijkstra and Prim's algorithm significantly reduced the required poles compared to the heuristic approach. The table illustrates that as fiber cable length decreases through algorithm optimization from heuristic to Dijkstra to Prim's, the design and deployment times are significantly reduced, leading to a faster and more efficient fiber network implementation. We then move to our last chapter to discuss the summary and conclusion. Overall, while manual and heuristic-based planning remains relevant for smaller and or resource-limited projects, algorithm-based approaches provide superior efficiency, cost savings, and scalability. The integration of algorithm-driven methods are the preferred choice for large-scale and complex fiber deployments. The study faces challenges such as terrain constraints, cost variability, and limited scalability, with assumptions made on losses and a single case study without a real traffic data. Future fiber network planning should integrate real-world geographical information system, or GIS data, AI-based modeling, and hybrid optimization techniques to enhance accuracy, adaptability, and deployment efficiency. Additionally, validating simulated results through field trials, ensuring regulatory compliance, and training planners with user-friendly tools will support scalable and future-ready network designs. This study underscores the significance of graph theory in solving real-world infrastructures challenges and lays a foundation for future research and implementation in more complex and larger-scale network scenarios. The methodologies and results presented here can serve as a valuable reference for engineers and researchers working on the design and optimization of fiber optic and other types of networks. Thank you for listening, and God bless.
Alright, dear panelists, this ends my 20-minute video presentation.
Emerson, do you have the videos, the simulation of your results?
Okay, I didn't record the video simulation, but I can show you on my screen right now on how to do the simulation.
Thank you.
All right. So first, I have this software with me. We call this AutoCAD, Autodesk AutoCAD software. This is the current software tool that most of fiber designers are using worldwide. So first, before we come up with initial fiber network design, it should start with data gathering. So if you ask me how did I get the data from a remote area, we used to have a street view. So I've selected this area because I find a street view available to this site. So I'm using a Google Earth Pro software for me to plot on or convert the drawings from AutoCAD to a KML or KMZ file format that can be read by this software. So to get the data, I used to get a street view. Whenever I drag this thing, it will show me the relevant information that I need to know on the field. That is to get the existing pole utility location, the current situation on the ground, whether should I install a new pole or propose a new pole. So I made this design for me to provide a fiber network design for high-speed broadband internet, particularly FTTH. It's a GPON solution that can be used for the LGU or for existing internet service provider. So this is how it looks like. So if I exit the street view, I should be able to see the map on top and able to get the street names accordingly. So right from this information I get from street view, I digitize it using the AutoCAD. So I should be able to get the pole locations, which are these ones. I've even placed my remarks whether what pole that exists on that particular area. So first, I need to do a heuristic plan. So what I did, I populate the segments, the possible routes that my fiber network can reach on, can go on. So that includes plotting the lines across all the streets that I can see, and next I have identified the proper node locations. So these are the node locations that I have plotted initially. So these are 100 nodes. Every node can able to feed 16 customers or 16 households of internet lines. So it uses a GPON technology, which has a passive component in between the network, as I have shown on my single line network diagram, and the electronic component will just be located at the cabinet where the OLT location is, the exchange side, and at the customer premise, or how we that's what we call the modem or the ONT. I have identified the OLT location somewhere in the middle, and that's where the active equipment will be, this one. So I've used this symbol logo to identify, to say that this will be my proposed location of the active equipment, the optical line terminal. That requires electricity and main uplink to the either exchange or to to another internet service provider who provides the internet connectivity. So now that I've got these lines with me, these fiber segments with me, I should able to populate my node matrix on Excel file format, which is this one. So this is pre-map. It has a formula already in place that I can be used to enable me to get the script. So I want to discuss first this Excel file. So on my video presentation a while ago, so this means that it's a weight of a segment. It's the distance between nodes. Like for instance, node 0 to node 0, this is common, so it should be 0. It doesn't have a distance in between. But from node 0 to node 1, it has 115 meters or units of distance. So how did I get this? There are two ways for me to get this distance. First, I can get it easily through this AutoCAD software. If I look at node 0 on my plan to node 1, which is this one, so if I add the total distances between this node, I just need to run a command on this software and it will tell me the distance. So I have 115 units of this distance, which I have reflected to this matrix. So from there onwards, I have populated all the sheets, the cells, I should say, and populated 0 for those nodes that doesn't have a distance in between. So like for instance, node 0, it has a connectivity between node 6. I'll show you on the screen. So node 0 to node 6, which is this one. Right, so I have to measure that, and it gives me 105 meters of node distance. Sorry, it should be 122. And aside from using AutoCAD, so this is 122 from node 6, and 474 units distance from node 21, as you can see on my initial drawings.
Okay. So based
Yeah.
on your computed distance, based
Mhm.
on the Excel sheets, so
Right, ma'am.
those values are input
Approximately.
to your algorithm.
Yes, ma'am.
So
Correct.
how did you use this one to the algo? Can you
Okay.
show us? Yeah.
Okay. So now that I have come up with this data, so I'll be copying this into the program, which is so by the way, I have used an online compiler. So those data, these values are then copied and pasted onto this content, to this script. So I just copied and paste it here. So this is my prims script, minimum spanning tree script. So we just need to copy paste that content into this script, and which is this one, and then we have to run the script, and it will show me these values, right? So I'll get these values and go back to the Excel file and paste that result here in this Excel file. So after pasting it, I should able to extract the weights.
Okay, good. Thank you.
Yeah. So on Prim's algorithm, I should able to get these values which I have presented on the video presentation. That's for Prim's and for Dijkstra. Using the same technique, we copy paste these values and put it onto our script for Dijkstra algorithm this time. So we have to specify here the number of nodes. I placed here the 100 nodes. So you just need to follow the
Emerson,
remarks.
okay
Yeah.
na ako. Okay na.
Ah, sorry.
So,
Okay, so I'll continue to my presentation. Hold on.
I think you're done. So, panels, any questions? Bakjen?
Hi, yeah. Good morning, Emerson.
Good morning, Ma'am Jen.
How are you right now, Emerson?
Good. I'm good, ma'am. It's currently cold here. It's a cold season po dito sa afternoon. So I just took
Nasaan ka ngayon?
sa Fiji Islands, ma'am. Fiji Islands.
Fiji, okay. So
Yes.
malamig o nga, ano? Australia, very near Australia.
Yes, we are near in
So,
Australia.
winter nyo ngayon.
Yes
Okay,
po.
anyway, yeah, I saw my recommendations and I believe you were able to comply, and you were able to address all the recommendations as far as my recommendations are concerned, no?
Yes,
So, based on that, I also have some follow-up questions, but would like to commend you for, managing the 100 node. But even though when I say 100 nodes and you try to select a specific site, diba? And also try to simulate, for example, an application that will require connecting, like for example, connecting 5 buildings. Is that how you conceptualize the entire routing system?
Yes, ma'am. So if we have to specify the node that we're referring on. So the node can be a building, a fiber access node, which I have used here on my case study, and it can also be an electronic component in between
Okay. So that's
buildings.
actually part. So maybe you can just include that in your
Okay.
discussion. No, ang sabi ko dito, how did you define the nodes in the site provided? Okay. So
Okay.
kasi 100 nodes yun, and I saw the points, no, yung mga nodes na nilagay mo, but I'm not really sure saan kakabit yun. Okay.
Okay,
So
noted.
so kung ano yung paki-define na lang yun sa ano mo. And then include in the discussion yung Dijkstra and Prim route simulations and results. So wala kasi yun. Like for example, some screenshots of your simulation a while ago, yung pinakita mo sa amin kanina.
Yes.
So that will help as well, no? Kung paano pinipili yung route for the second, third point up to the 100, no? And the number of routes versus time, meron ba tayo?
Yes,
Versus time?
yes, ma'am. So I've shared that, presented that on my recorded video.
The actual metric naman na nakalagay, ano?
Yes
Kung
po.
ano yung ginamit mo na versus ano.
Mm-mm.
Tapos, equipment specs, requirement for 100 nodes. Kasi 100 nodes medyo mabigat, no? Pero naglagay ka ng cabinet kagad nakita ko. So, yung nilagay mong cabinet, pakilagay naman yung specs, no?
Okay.
That can accommodate the 100 nodes. And how did you define nodes? Okay na yon. Yung is 5 building design applicable for 100 nodes? Actually, the answer is no, no? Hindi naman pala 5 buildings, so iba-iba pala talaga siya.
Yes.
So, addressin ko na lang tong part na to.
Okay, thank
Okay?
you.
So, that's all for me. Thank you for
Thank you,
that
Jen.
design, Emerson.
Thank you, ma'am.
Thank you, Bakjen. Dean, kayo po.
Si Dean daw po comment na lang siya.
Ano po, comment na lang. Okay.
Apa.
So, yung sa akin naman, I don't have any questions kasi ang concern ko lang is the simulation and you showed it a while ago. So, I'm good with that. Okay. Doc Marlon, yun lang ako. Thank you.
Okay.
By the way, yung conceptual framework lang pala yung comment ko, ha? So,
Yes,
sa conceptual framework, you need to put your input. Ano yung input ng system mo? Example, yung distance. So, I think yung input mo is the distance. And then yung process, keywords of the two algorithm, and then yung output. So, yun yung shortest path, di ba? Yun yung magiging
Yes.
output mo. So yun, pa-revise na lang yung conceptual framework ha.
Noted, ma'am.
Yun lang naman. Thank you. Thank you, Doc Marlon.
Okay po. Sir Emerson, we'll put you sa waiting room muna as we decide.
Sure po.
Thank
Sure.
you.
I'll wait for it.
Recording in
Day
progress.
7, Day 1.
Undergrad, ma'am.
Undergrad, yes. Nasa table ko, nasa harapan mo.
Sige po.
Hanapin mo na lang. May file dyan nakakompile July 17, ha?
Okay po.
10 a.m. Thank you. Pa-picture na lang. Picturean mo, then send mo sa kanila.
Okay po.
Thank you.
Ayan. Doc Jo?
Okay. So Emerson, upon the deliberation of the panels together with your advisor, so we accept your final presentation with minor revisions. Congratulations.
Thank you,
The
ma'am.
recommendation
Thank you.
will be given to you by Doc Marlon later. Okay, so bibigyan ka niya ng copy ng recommendations mo. Okay? For the conformity of revision, so you need to satisfy all the recommendations. Then, tsaka kami pipirma ng conformity. Okay? But see to it that your advisor will sign it first before you route it to the panels. Okay?
Noted, ma'am Jo.
Congratulations,
Thank you po.
Emerson.
Usap na lang tayo, Sir Emerson.
Yes po.
Congrats,
sir.
Emerson.
Thank you, ma'am Jen.
Congratulations.
Thank you po.
Sige po.
Parang settle ka na.
You can, ano na po, Sir
Okay,
Emerson.
I'll leave the...
Thank you very
ma'am.
much.
Have a good day po.
Okay po.
Bye-bye.